For the last part of this section on optimization, which I call 14.7 part 3, we're going to go back to this example from 5a that we've kind of done in pieces. We looked at local extrema, we looked at absolute extrema. But there was this special case of absolute extrema problems back in single variable calculus. And specifically, that was absolute extrema if f is continuous on a closed interval. That was a special case. That was actually easier than the last type because it gave us a way to validate. Sometimes the hard part back here was how do we validate that we actually have an absolute extremum because we don't have a set test for that. Well, in this special case, we do have a set test. So the case is twofold: continuous, closed interval. In the case of a continuous function on a closed interval, all we have to do, this is the closed interval method, it's in section 3.1, we find the values of f at its critical points, which we did back here already, so let's just, we find the critical points. So we said that our f value, our f of x, is 3x to the fourth minus 16x cubed plus 18x squared, and we got critical numbers of 0, 1, and 3. And we had to do all the sign chart and everything. Here, there's nothing about a sign chart. We're just going to find the values of f at the critical numbers. And so that means we just find those critical numbers, and we just evaluate our function at those critical numbers. So we put in 0 into this function. We get 0. We put in 1, and I'll let you do that. You're going to get 5. And if I put in 3, I'm going to get negative 27. Okay. Step 2 says find the values of f at the endpoints. So these were the critical numbers. And then we also had to look at the endpoints. The endpoints in this example that I've given you, I'm looking for absolute extrema on this closed interval -1 to 4. So I'd have to put in -1 and 4. These critical numbers are all in that interval. And we put -1 into our function, and we put 4 into our function. And if we do that, we're going to get, for -1, we'll get 37, and f of 4 would be 32. Now it says the largest of these is the absolute max, and the smallest is the absolute min. Largest along the way here is right here, so this is our absolute max. And the smallest is here, absolute min. And we don't have to do any validation. We don't have to look at the first derivative and see where the function is increasing and decreasing. This is all we would have had to do. So this is kind of our simpler case. And the reason it works is because by the extreme value theorem, if you have f that's continuous on a closed interval, that guarantees that you will have an absolute max and an absolute min. And the only place that those can occur are at critical numbers or at endpoints. So if you know there's a max and it's got to be at one of these places, and you know there's a min and it's got to be at one of those places, you just find the biggest and the smallest. Okay, what we're doing graphically here is here's a graph of our function. It doesn't have an absolute max, it goes forever. It does have an absolute min, but in this problem here, we're only looking at -1 to 4. We stop here and we stop here. And so in this case, we do have that absolute maximum value, absolute minimum value. Okay, so when we have this special case of continuous on a closed interval, then we don't have as much validation to do. Now let's go look at that in the function of two variables scenario. Suppose you wanted to find the absolute extrema of a continuous function on a closed domain here. In this case, instead of the domain being a closed interval, like that, when we talk about a closed domain, our domain is a set in X, Y. So when we talk about a closed domain, we are talking about some region that includes all of its boundary. The boundary is similar to what happens here at the endpoints. So if we're asked to find the absolute extrema in between 1 and 4, including 1 and 4, that's the same as taking a function of two variables and saying, find the absolute extrema on this closed domain, which means on the boundary, which is the yellow part, and then everywhere inside. So here's how we're going to do it. This is the same idea. First, we're going to look on the inside. So we're going to consider the inside of the domain. So in this case, we're being asked to find the absolute extrema of this function here. Now let me actually draw that. Even better, I let the computer draw it. This is a circle, of radius 1. But in this case, we're talking about less than or equal to. X squared plus y squared equals 1, that's the boundary. If we're talking about x squared plus y squared less or equal to 1, then we're including all of the inside as well. So the inside there is like the inside of that interval from 1 to 4. So the first thing we do is we consider the inside. We find critical points inside the domain. And then we're going to look at what happens on the boundary separately, just like we did. So critical points here, fx equals 0, fy equals 0, is 2x equals 0 and 4y equals 0 from here. And so we just get the point 0, 0. That's our only critical point. Okay, now let me make a little table down here. Similar to what we did in the 5A problem there, we're going to look at critical points. And then for right now, I'm just going to call it endpoints, but we're going to talk about that. That's going to be something new. So our only critical point was 0, 0. Put that into our function f of 0, 0, and we get 0. This function is continuous. This is a closed domain. It has to have an absolute max and absolute min. It can either occur at critical points. So this is what we found. Here's the only critical point that we found. And we found that the functional value there was 0. Or it'll occur on the boundary. So let's consider the boundary now. As I said, this is like our so-called endpoints. So the boundary is just the circle itself. So we replace the inequality with an equals. And so we're constraining our function to just satisfy x squared plus y squared equals 1. So if we do that, we can incorporate this constraint into our equation, just like we did in the previous, in 14 section part 2. We incorporate the constraint. And so we're going to get f of x and y equals, let's see, I'll just solve for x squared here. X squared equals 1 minus y squared. So I'll substitute that here. I don't actually need to solve for x because I'm substituting for x squared anyway. So x squared is 1 minus y squared. And so I get 1 plus y squared. Now that's my function. I like to, notice how we eliminated one of the variables? So I like to call it some function of y now. Just to remind myself, really, once I've eliminated one of the variables, I'm back to Math 5A. I'm back to single variable calculus. And it's really important for us to understand something. This is my function. This is this function, only it's this function when we're constrained to that circle. Meaning, if I take any point in here, let me just randomly take a point here. Let me just take this point here, -1, 0. If I put -1, 0 into f right here, f of -1, 0, I get 1, 0, I get 1. That's the same thing I'll get if I take this point where y equals 0 and I put it into this function. I get g of 0 equals 1. It's the same functional value either way. That only works, so these are interchangeable. This is simpler, but these are interchangeable if I'm on the boundary. If I'm not on the boundary, for instance, let me just take this point, 0, 0. These are not interchangeable then, because 0, 0, this function here, f of 0, 0 equals 0, but g when y equals 0 is 1. So they're not the same. So one more time, what does this represent? This represents the same as this function, only if I'm putting in points on this boundary. So that's why this is like when in the 5a problem, when we plugged in the 1 and plugged in the 4 as our endpoints, we've essentially plugged in our endpoints. Now what we want to figure out is, okay, well, this takes on infinitely many values. I want to know what's the biggest one and what's the smallest one. I can't possibly plug in every point here. But I can find the maximum minimum of this. So I would be finding, of all these points, the one that gives me the biggest output and the one that gives me the smallest. So really what happens here is this becomes a 5a problem. That means the single variable calculus inside our problem, which is I'm going to try to optimize g of y equals 1 plus y squared. And I have actually a closed interval. I'm not looking at all values of y everywhere. I'm only looking at points on this curve. And points on this curve have y values that go from -1 to 1. So y is between -1 and 1. And so at this stage, we're back to the previous page. We can just use the closed interval method. I'm going to work this problem completely. This problem within a problem. So I'm doing 5a for a minute. We'll come back and see what that means about 5c in just a sec here. So how did we do this in 5a? We found the critical numbers by taking the derivative, setting it equal to 0. So that was my critical number. Then we just evaluated our function. Whoops, our inputs are y's. Our function is g of y at the critical number and at the endpoints. The endpoints here are -1 and 1. Where am I putting that? I'm putting it into G. I'm not looking back here at all. This is my function I'm trying to optimize. I put the critical number in here, I get 1. And I put the endpoints in here, and I get 2 for both of those. Okay, so what does this mean? This means when I'm on the boundary, so anything that's blue here is when I'm on the boundary. So it might even be nice to make it blue. That blue function is just when I'm on the boundary. So when I'm on the boundary and y equals 0. When I'm on the boundary and y equals 0. That's these 2 points. When I'm on the boundary and y equals 0. In both of those situations, I got a functional value, an output of 1 at both of those. What does this tell me? This says when I'm on the boundary and y equals -1. When I'm on the boundary and y equals -1. That's going to be here. The functional value that I get there is -1. This tells me when I'm on the boundary and y equals +1. That's going to be up here. The output of that function is 2. Oh, I made a mistake back here. The output of this function is 2. The yellow output was also 2. I got -1 on accident from there, but that's 2. Okay, here we go. Okay, now you don't have to write this in here, but here's what we're actually doing. I said we were going to evaluate at the critical points and the so-called endpoints, which by that I actually mean on the boundary. And what we found that we didn't end up looking at all the points on the boundary. We only had to look at the ones where we got the highest and lowest points. And so at this point here, at -1, 0, and at 1, 0, we got the output of 1 at both of those. At the yellow point down at the bottom, which is 0, -1, we got a functional value of 2 here. And then at this purple point, which has coordinates 0, 2, we got an output of +2. And so we just compare, whoops, we just compare these values here. The biggest one we see is 2. It happens in 2 places, but the biggest that we see is 2, so our absolute maximum is 2. And the smallest of these numbers is 0, so the absolute minimum is 0. You can keep track of all the points in a little table like this. I actually like to keep track of them on the picture because you're going to see in another example that there's another example video in the module that sometimes there's a lot of points that we're checking and it's hard to keep track of them. So I usually try to keep a picture of it on the video. All right, now I want you to understand what you're really doing here. So I've got a picture. The function x squared plus 2y squared, that's this paraboloid. It's an elliptical paraboloid. And if I just said find the absolute extreme of this function without saying any sort of constraint, it has an absolute min here, and it doesn't have an absolute max because it goes forever. If I said, let's just look on the boundary, okay, so we're just going to put in points on this boundary. So if I just put in points on the circle x squared plus y squared equals 1, so something like this. This is my circle, x squared plus y squared equals 1. I put those into the function, and I'm getting all these points here. Okay, so I would just be looking at all the blue points on the surface. When we say x squared plus y squared, so that's x squared plus y squared equals 1. But we're actually supposed to be looking at x squared plus y squared less than or equal to 1. And so that means we're not only looking at that blue boundary, we're looking at all this in here. I don't know how well you can see that. It doesn't look like it's turning purple. I'll fix it in just a minute. So that means we're not looking at any of this up here. Oops. Okay, so this got a little messy here, but I think you get the idea. So on this problem then, we're finding the absolute extreme of this piece. And what we found, what it turned out to be, is that the absolute minimum was 0. That occurred at 0, 0. That's here. That's the absolute min. That's where the min is. The absolute min is 0. Then when we were coming over here and looking at the boundary, we found these two green points right here. Those were where x equals plus and minus 1. That was over here and back behind there. The purple point is when y equals 1 and x equals 0. So that's up top here. My drawing is a little unclear. This green dot is behind there on the negative x-axis. And then the yellow point corresponds to when y equals negative 1 and x equals 0. X equals 0, y equals negative 1. That's putting us up here. So the maximum occurs at these two values, and that functional value is 2. The absolute minimum is here, it's 0. What about the green points? Well, those aren't maximums or minimums for this whole surface. If we're just sticking to the boundary, then those would be absolute minimum. But when we incorporate the inside, then they're neither max or min. Okay. So how am I going to know this is this kind of problem instead of the 14.7 part 2 kind of problem? Here's the key right here. Here's how you're going to know. You're going to have an inequality. If you see, so you're having some sort of closed domain. I'm not just doing a constraint equation that I can incorporate. I have an inequality. So we're looking at a whole region. So when you do that, you have to do two things. You have to check critical points inside, and then you have to consider the boundary. Right? There is another example. There's another example video. I'd recommend you look at it because it's got more going on than this one. It's the same idea, but the domain is more complicated. The domain, I can't remember what that domain was, but you'll see domains where it's maybe something like this. Then you can't incorporate it in a single equation like this. You'd have to break it into 3 pieces. So take a look at that example. Then I would encourage you in the note outlines, if you printed them or take a look at them, I summarized 14.7 because I've broken it into 3 pieces for us, right? So on one sheet of paper there, I kind of summarized the different kinds of absolute extrema problems, local, absolute, and absolute on a closed domain. All right. Okay, good luck with these problems.